Welcome to another Environmental Systems and Societies video. Today I'll take you through a practical activity where we test water for dissolved oxygen. I'll show you how we set it up in the lab, as well as where we went out and collected our samples. Let's get into it. So the first site we've chosen to investigate our water quality is this pot with a bunch of aquatic lotus plants growing in it. And here, inside this water, we expect to find a bunch of microbes. We might also find some frog tadpoles. I can see algae growing in here. And of course, we have the aquatic plants themselves. So this will give us an opportunity to see how the different organisms in the aquatic environment interact and affect the dissolved oxygen level. The next site we've chosen to investigate is another pot full of water, but it has a different species of plant growing in it. Again, when I look in this water, I can see all kinds of things growing. I see algae, I can see little things swimming around in the water, and we want to see how the interaction of those living organisms affects the dissolved oxygen. The next site we're going to investigate is this fountain right here in front of school. As you can see where the water falls into the pool, we've got all these bubbles happening. We want to see if that falling turbulent action affects the dissolved oxygen content in this water source. And last but not least, the last site we're going to investigate is this portion of the same pool of water. And this spot is as far away as we can get from where the water falls in to the pool over there with all the bubbles. So this water is very slow moving. See, it still has aquatic plants in it, but we've walled off the fish, so the fish can't come in here at all. We're going to see if there's a difference in dissolved oxygen of this site, the falling water, or two different pots, different species of aquatic plants living in it. Okay, I'm back inside after collecting the water samples, and I've got all of my samples here in these bottles. Notice I've got the bottle and the cap and the syringe all labeled with the same letter. That prevents me from contaminating other samples with the same equipment. So this is a standard 20 milliliter syringe. Most science labs will have it. This is just a plastic sample bottle. I've labeled it using whiteboard marker because it's easy to clean off. Right? So I've got my 5 samples here, all with their individual pieces that they need. I've also got a test tube rack for each of those sites. And I'm going to take 4 samples at each one, or I'm going to run 4 trials at each one to check for consistency in my data. That should help ensure that I have data that is reliable. Back here, I've got a couple of different water test kits. We just bought these from School Supply Company. I believe they're manufactured by Hanna Instrumentals. So what do we have here? Well, I simply follow the instructions in the manual and walk students through it. Before we get too far into it, I want to make sure that I have the things from the kit that I need for this specific dissolved oxygen test. There's a lot of stuff in here that I don't need for this, and it gets confusing if I've got it all sitting out. So what I've done is I've read through the instructions first, and then I've pulled out the different reagents that are needed just for this test. So here I've got the 3810 dissolved oxygen titrant solution. I have the manganese sulfate solution. I have the alkaline azide reagent. I have the sulfuric acid. I have the starch indicator. I have my little 1 milliliter syringe. And then I have a glass test tube that's clean and has an airtight stopper on top for my sample. What I am doing here is I'm reading and following the instructions in the manual that comes with a test kit. Rinse your glass bottle 3 times with your water sample and fill it to overflow. So this is my sample. I'm choosing my sample E, and I'm simply going to come over here to my sink. I'm going to add enough of my sample that when I invert it a few times, I'm making sure that the entire interior surface area of the test tube has interacted with my sample. I've poured it out, and now I am pouring it until it overflows so that there's no air bubbles in my sample bottle. That's the first step. You drop that right here. And again, I'm dealing with water. These are impervious lab benches, so I don't have to worry about any kind of spills. Right? Step 2, add your dropper until some of the sample comes out. Once it spills over, you know it's good to go. Right? Then, step 3, remove the stopper and add 5 drops of manganese sulfate solution and 5 drops of alkali azide reagent. Here's my manganese sulfate solution. I'm going to add 1, 2, 3, 4, 5. Very straightforward. Here's my alkali azide reagent. Again, 1, 2, 3, 4, 5. Now, I don't know if you can see this on the camera or not, but a precipitate has begun to form. Next step, add a little bit more of your sample, and here's where this syringe comes in handy. I've got some of my sample in here, and I'm just going to add it until my test tube is full and overflowing a little bit to put your stopper back on so that it spills over again a little bit. You might want to do this on paper towels. Then I'm going to mix it a little bit. I'm going to put it back. I've got this cloudy solution, and I'm going to let it sit for a couple of minutes until that precipitate begins to fall to the bottom of the test tube. I've let my sample sit for a few minutes, and as you should be able to see, the top part of the sample is clear, and the bottom part has all of this precipitate in it. So at this point, I take the stopper off, add 10 drops of sulfuric acid solution. So here I have my sulfuric acid solution, and I'm going to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I probably did that a little faster than I needed to. Try to be a bit more careful and precise to ensure accurate data when you're doing your labs. I'm going to stopper it again, and then what I'm looking for this time, I'm going to take my sample and I start to shake it and mix it. It becomes less cloudy. I've still got some cloud up here, so I just need to make sure that I'm turning it back and forth to get it to really start to mix. And if you can see this sample clearly, it's losing the cloudiness, but it still maintains that yellow color. So it goes from being kind of this milky, yellowish, orange, cloudy solution to a clear yellow solution that frankly looks like a urine sample. So now I've got my clear yellow sample. You want to rinse the plastic vessel with the solution in your test tube. So what I would recommend you do, you're going to take the stopper off, and you don't have to fill this. You're just going to add a little bit. You're going to kind of rinse it around because the idea, or swirl it around, the idea is that you want to make sure that the plastic vessel is just interacting with your sample. Fill to the 5 milliliter mark. Make sure that I have exactly 5 milliliters. Add 1 drop of starch indicator, and what you should see when this starch indicator hits the yellow solution is an instantaneous color change. Boom. It looks like the iodine clock reaction, if you've seen that before. Now, this whole solution is deep purple. That's why the starch is an indicator. Next step, take this little micro syringe. This entire syringe holds only 1 milliliter of solution. Take this syringe, and we're going to pull this dissolved oxygen titrant solution into our little micro syringe. Put it in and pull it all the way up until the plunger is at 0.0, which means I want to make sure that there's no air in this thing at all. So there, I've gone beyond what I need to do. I'm going to move my plunger into position here so that it's very precise. The bottom of my plunger is on the 0 mark. Now, I've added my special little airtight tip, and what I'm going to do is I'm going to go kind of drop by drop, and I'm going to titrate it. And as soon as this dark purple liquid goes colorless, I'm going to stop adding this titrant solution. And usually what will happen is you'll get 1 or 2 drops where it temporarily goes colorless, or the color becomes a little bit paler. And when that is the case, you're very close to that endpoint. My solution is completely colorless. It's colorless. I've swirled after each drop to make sure that it's well mixed, right? Then I'm going to read the results here on my little micro syringe. I'm at 0.82 milliliters of this titrant solution. So 0.82. Read off the milliliters of titration solution from the syringe scale and multiply by 10 to determine your oxygen parts per million. So if I have 0.82 milliliters is the indicator here on my syringe, that means this sample contains 8.2 parts per million of dissolved oxygen. Now I've completed my dissolved oxygen test. I'm going to do that for every single sample at all of the sites, and I'll organize it into a data table, probably with a column where I simply record the measurement off this syringe, and then the next column over, I just multiply each of those cells by 10 to give me a parts per million indicator. From that point, you can begin to process your data and determine whether there are differences in dissolved oxygen between the different locations that you've tested. You can also test a variety of other factors in your water samples. You can look at alkalinity. I've got a bunch of test kits here for phosphate levels. We can look for chlorides. We can look at iron. We can look at sulfites, test for water hardness. I can use things like a light sensor and a temperature sensor, so we can look to see how the light level or the water temperature affects dissolved oxygen. If you're doing this in the field where you actually have a moving body of water, you could also measure flow rate and see if dissolved oxygen is connected to how quickly or slowly your water source is moving. There's a whole range of activities you can do with this, but this is a laboratory setup. But what we've done here is also very applicable for field investigations associated with your internal assessment. So that's it for testing for dissolved oxygen. I hope you found that helpful and a little clearer than some of the instructions you'd find just in a standalone test kit. If you did, please consider giving this video a like and subscribe to my channel. You'll also find a lot of other resources for environmental systems and societies at my website, mrcreamerscience.com. Happy learning.